Okay, let's unpack this. Close your eyes for a moment and just imagine a world where you could truly keep an eye on what matters most.
Like the well-being of an aging parent, maybe.
Exactly. Or the adventures of a child playing, or even the security of a really sensitive area.
Right. Important stuff.
Now, imagine doing all of that without a single intrusive camera pointed at anyone,
Huh.
and no fussing with, uncomfortable wearables that need charging or you have to remember to put on.
Yeah, the ones people forget or just don't want to wear.
What if there was a way to see every important activity, every subtle movement, without actually seeing anyone at all? It sounds a bit like science fiction, doesn't it?
It really does. Something futuristic.
But today, we're diving into a technology that makes this seamless blend, this coexistence of deep privacy and real safety. Well, not just a dream, but a very real, incredibly practical reality. Welcome to the Deep Dive. We're here to take complex, cutting-edge research and, well, break it down into the essential bits, giving you that shortcut to being genuinely informed. Today, our topic is wireless human activity recognition, or HAR for short. And this isn't some far-off tech. HAR is evolving super fast, and it's already reshaping so many areas.
It really is. Think about healthcare, especially aged care, where, independent living is so crucial.
Absolutely. Or think about keeping an eye on kids discreetly without being overbearing.
Or even security in places where cameras just aren't practical or allowed. Restricted zones, maybe?
Right. So HAR is already influencing things like smart homes, how elder care facilities work. It's quietly becoming part of the background.
And this brings up a really fundamental question, I think. How do we get reliable, continuous monitoring in these sensitive situations without just throwing privacy out the window? Or without making people constantly interact with the device, like remembering to wear something?
That's the core problem.
It is. Because current solutions, they often force this uncomfortable choice.
Yeah.
You've got vision-based systems, cameras.
Yeah, the obvious one.
They can be super accurate, which is great. But wow, the privacy trade-off is huge. They record actual video. People find that intrusive.
And they can be blocked, right? A curtain, bad lighting.
Totally.
Oh.
Obstructions are a killer for cameras. Low light, fog, smoke, furniture in the wrong place, suddenly they're useless.
Okay, so what's the alternative? Wearables.
Well, yeah, wearables. They definitely preserve privacy better because the data sticks with the person. But they have their own pretty significant practical issues.
Like battery life. Always charging things.
Battery life is a big one. Comfort, too, wearing something to 247. And people lose them or forget them.
Especially the people you most want to monitor, maybe the elderly, kids.
Exactly. So for continuous long-term monitoring, wearables are often just not ideal. They demand too much from the user.
That's such a critical point, and that tough choice, that gap in what current tech offers, that's precisely what this deep dive is all about today. Our mission is pretty clear. We're going to introduce you to tinyRadar. It's a novel, kind of ingenious system that tackles these exact challenges head-on, offers a really compelling solution.
Yeah, it's a fascinating approach.
We're going deep into a scientific paper that unveils this system, focusing on its really unique approach to real-time, multi-target human activity recognition.
Multi-target is key there.
Definitely. It uses radar, advanced AI, all packed onto these tiny edge computing devices.
Super compact.
So settle in. We're going to unpack how this works, what makes it so effective, so efficient, and what it could genuinely mean for the future of discreet, smart, and importantly, private monitoring. Okay, so to really get why tinyRadar is such a big deal, we need to start at the beginning. Why use radar for HAR in the first place?
Right. Because most people, when they think sensing movement, they think cameras. Or maybe motion detectors, the simple PIR one.
Yeah, exactly. But radar, it's fundamentally different, isn't it? And that difference seems absolutely key here, especially for the privacy aspect.
It is profoundly different. Radar works on electromagnetic principles. It sends out radio waves and listens for the echoes. Unlike cameras, which need light, radar doesn't care.
Doesn't care about light. So day or night, bright room, dark room.
Makes no difference. It sees using its own waves. That's a huge advantage for reliability.
Yeah.
And what's maybe even more powerful is how robust these waves are.
Yeah.
They can actually penetrate many materials that would totally block a camera.
Like what kinds of materials?
It's like fog, thick smoke, even everyday things like curtains, blankets, maybe even thin walls or a sheet of paper. Radar can, to a large extent, see right through them.
Wow. Okay, so you get robustness in places where cameras just wouldn't work. Obstructed views, messy rooms.
Exactly. It means you could place a tiny radar sensor pretty discreetly, maybe behind something, and it would still work perfectly.
Yeah.
It doesn't need that clear line of sight.
That makes it really non-intrusive then. And here's the part that I think it's really interesting for anyone worried about privacy in, say, a smart home or a care facility. Radar protects privacy inherently. How does it do that? It's not just not taking pictures, is it?
No, it's much more fundamental. It's about the type of data it captures. Instead of visual image, a video feed showing faces, clothes, details.
Yeah.
Radar processes what's called sparse point cloud data. Imagine. Not a photo, but more like a moving constellation of little dots or points in space.
Okay, like stars moving around.
Kind of like that, yeah. Each point represents a reflection, maybe indicating position or movement in a limb, a torso perhaps. But critically, none of it looks like a person. You can't tell who it is.
Ah, so it's abstract. The identity is just gone from the data itself.
Exactly. It's the pure essence of motion and presence, stripped of all the visual identifiers that raise privacy flags. It's privacy by design, baked right into the sensing method. You get the what, the activity, without the who in a visual sense.
That's a brilliant analogy, a constellation. So abstracting the data makes visual ID impossible. And I'm guessing that that approach also helps the system itself, computationally.
Precisely. That's another massive advantage, because you're dealing with this sparse, abstract data, just points, and they're motion vectors, essentially not high-res video.
Right, video is huge data.
Exactly. The computational load for processing is way, way lower. And that's absolutely critical when you're talking real-time analysis on small, low-power devices.
The edge computing aspect.
The edge computing aspect, yes. If you want to deploy these sensors widely, they need to be efficient. They need to do their job without needing massive computing power or constantly streaming data. This low computational footprint is core to tinyRadar.
But this level of privacy and efficiency wasn't always the case with radar, was it? I mean, radar used to be big military stuff.
Oh, absolutely. Historically, radar was bulky, expensive, power-hungry, not something you'd put in the living room.
So what changed?
The game changer has been the rapid advancement in semiconductor technology. Miniaturization. This has led to the creation of much smaller, compact medium-wave radar hardware.
Millimeter wave.
Millimeter wave, yes. These operate at higher frequencies, allowing for smaller antennas and higher precision, making them really appealing for HAR. These tiny radar chips are the heroes here. And it's not just the hardware shrinking. This miniaturization happened alongside huge improvements in machine learning algorithms. AI got smarter and more efficient.
Ah, perfect storm.
Exactly. The algorithms became much better suited to run on this kind of resource-constrained hardware. What once needed a server rack can now, potentially, run on something tiny.
So small hardware meets smart, efficient AI.
That's the synergy. That's the foundation tinyRadar is built on. It turns this powerful sensing tech into something discrete, intelligent, and embeddable.
Okay, so the tech evolved. But even with smaller radar and better AI, earlier radar-based HR systems still had problems, right? Limitations.
They did. And understanding these is key to seeing why tinyRadar is innovative. One of the biggest headaches for researchers was the fixed time window problem.
Fixed time window, what does that mean?
It means many systems were designed to look at activity data in fixed chunks of time. Say, analyze everything that happens in a 5-second window, classify it, then look at the next 5 seconds.
Okay. Yeah, why is that a problem? Seems logical.
Because real human activities don't fit neatly into fixed boxes. Think about it. An elderly person getting out of bed might take 30 seconds, maybe a minute, slowly, deliberately.
Right.
If your system's window is only 5 seconds long, it just sees tiny, seemingly unrelated movements in each window. It never pieces together the full getting out of bed action. It might miss it entirely.
Or it might misinterpret it.
Exactly.
Yeah.
Or worse, generate false alarms. Conversely, what about a fall? That's super fast, maybe happens in 1 or 2 seconds.
Yeah,
If your window is too long, say 30 seconds, that quick fall event gets drowned out by all the normal movement or rest data around it in that window. Detection gets delayed or missed.
Ah, I see. The real world has different rhythms, different speeds. A fixed window can't capture that nuance.
Precisely. It's like trying to capture a quick photo finish and a long, slow sunset with the same fixed camera exposure time. You mess up one or both.
That fixed window thing sounds like a real barrier for practical HAR. So how did researchers try to get around it before tinyRadar?
Well, they developed more complex approaches. Some use convolutional neural networks, CNNs, analyzing things like 2D micro-Doppler spectrograms.
Micro-Doppler. Sounds complex.
It is. It's like a fingerprint of movement based on Doppler shifts.
Mm-hmm.
Or they used 3D point cloud data over time. These methods could be effective, but often they still relied on those fixed observation windows just with fancier data.
Still stuck with the window problem.
Often, yes. Then came attempts like slow-fast CNN networks. The idea was clever.
Yeah.
Use two parallel CNNs. One looks at sparse frames over a longer duration, the slow path, to context, and the other looks at dense frames over a shorter duration, the fast path, to catch rapid changes.
Okay, trying to get the best of both worlds.
Trying to? Yes. And it did improve accuracy sometimes. But the cost was a big jump in computational complexity and memory needed. Double the networks, roughly double the work.
Making it less suitable for small edge devices again.
Exactly. Less ideal for the edge. Then you had hybrid approaches using CNNs for spatial stuff and maybe temporal convolutional networks, GCNs, or LSTMs for the time aspect. Again, promising, but often still quite memory hungry.
So the core challenge wasn't just seeing motion, but understanding its duration and speed efficiently.
You've nailed it. How do you understand the time element flexibly, without rigid windows, and do it in a way that's light enough for edge computing? That's the niche tinyRadar carved out. It was designed from the ground up to be adaptable and efficient in exactly this way.
And it definitely carved out that niche. Okay, having set the stage with the challenges, let's formally bring tinyRadar into the spotlight. This is pitched as a genuinely smart, elegant solution for real-time HAR.
It really is.
Yeah.
At its heart, tinyRadar combines a very specific radar sensor chosen for its capabilities with a processing unit that's powerful but also really compact. And it uses advanced AI to make sense of it all.
What are the core bits of hardware then?
The eyes. The sensor doing the hard work of seeing the environment is the Texas Instruments IWR6843 radar board. That's the specialist part.
Oh, okay.
The pane, doing the intelligent interpretation, the AI inference, is actually a standard Raspberry Pi 4.
A Raspberry Pi. Wow, okay. So accessible computing power.
Exactly. It's this pairing of sophisticated sensing with readily available efficient computing that makes it practical for edge deployment.
And remember that frustrating fixed time window problem, the one that struggled with slow versus fast actions. How does tinyRadar get around that?
This is where it's really clever. The paper states it's explicitly trained on activities of varying durations.
So it learns the different timings directly from the data.
Precisely. It's not forced to fit movements into artificial time boxes. It learns to adapt to different speeds naturally. It's like, instead of forcing a square peg into a round hole with fixed windows, tinyRadar is designed to understand the rhythm, the flow, the actual narrative of the movement, no matter how fast or slow.
So it can recognize that slow going to bed sequence over minutes and the sudden fall that takes a second?
Yes, because it's learned the temporal signature, the characteristic timing of both types of activity during its training. It's adaptable by design. And the performance numbers they report are genuinely impressive, especially for an edge system.
Like what kind of accuracy are we talking?
They report 93% real-time inference accuracy, and that's across 8 distinct activity classes.
8 classes? What sort of activities?
Things that are really relevant for monitoring: falling, getting up from bed, going to bed, jumping, sitting down, standing up, walking, and just resting. Critical stuff.
Wow, that's quite specific. And how fast can it classify?
It classifies each activity frame, each little snapshot of movement data, within about 10 milliseconds.
10 milliseconds. That's incredibly fast. Truly real time.
Absolutely crucial for things like fall detection, where speed matters.
And the AI model itself, is it huge?
Nope. That's another highlight. The model size is just 311 kilobytes.
311 KB. That's tiny, like smaller than a typical photo file.
Exactly. Very compact, very efficient. And here's another really important feature. It's designed for multi-target HAR.
Meaning it can track more than one person at once.
Yes. It can simultaneously track and classify the activities of several people in the same space.
Okay, that's a big deal. So a busy room, a care home, common area, it can tell what multiple people are doing.
That's the capability, yes. It can distinguish between individuals and their activities concurrently. And it goes beyond just saying someone is walking. It also provides precise range data, the location for every target it identifies.
Along X, Y, and Z axes, so full 3D positioning.
Full 3D positioning, yes. It tells you where each person is in the room, along with what they are doing.
Okay, let's connect that to the real world. Smart homes.
Think about it. Your home doesn't just know if you've fallen, but exactly where in the kitchen near the stairs.
Or knowing a child is playing in one specific zone while an elderly parent is resting in another.
Precisely.
Yeah.
All without cameras. It enables a truly aware environment that's responsive, but also deeply respects privacy. It knows the situation without needing to see you visually.
Okay, we get the what and the why. Impressive results, solves big problems. Now, let's pull back the curtain. How does tinyRadar actually do this? How does it sense and process the data? It starts with the radar board, right? The IWR 6843.
That's right, that's the eyes. It uses a technique called frequency modulated continuous wave, or FMCW radar.
FMCW. What does that involve?
It involves sending out signals called chirps. Think of them as very quick sweeps of radio frequency. The radar transmits these chirps using its 3 transmit antennas, TX antennas, like casting an invisible net.
Okay, sends out chirps. Then what?
Then its 4 receive antennas, RX antennas, are constantly listening for the reflected signals, the echoes bouncing off objects, including people.
Got it. Caches the echoes.
These received signals are then mixed with copies of the original transmitted signals. This creates something called intermediate frequency, or IF signals.
IF signals.
Oh.
And these contain the useful information.
Exactly. The frequency and phase of these IF signals hold the key data about a target's range, how far away it is, and its velocity, how fast it's moving towards or away from the radar.
Wow, okay. All encoded in that mixed signal.
It is. These analog IF signals are then quickly digitized by an onboard analog-to-digital converter, an ADC. The result is stored as a radar cube matrix, basically, the raw digital data ready for processing.
So that radar board, the IWR 6843, isn't just a dumb sensor passing raw data. It does a lot of processing itself.
Oh yes, it's quite sophisticated. It has its own onboard signal processing chain using dedicated components. There's a hardware accelerator, HWA, a digital signal processor, DSP C67X, and a Cortex-R4F microcontroller. It's like a mini processing factory on the chip.
A factory. Okay, walk us through the production line. What happens to that raw radar cube data first?
Right, step by step. First, the rangefinder stage. The hardware accelerator, the HWA, performs a fast Fourier transform, an FFT, on the data. This is the range FFT. Its job is to figure out the range of any potential targets, how far away things are.
Okay, range found. What's next?
Next, the DSP takes over. Think of it as the map maker. It uses a technique called Capon beamforming to create range azimuth heat maps. This gives a clearer picture of targets across range and angle like a rough 2D map.
But maps can be noisy.
They can. So the DSP then acts as a noise filter. It applies a 2-pass CFR queso operation, constant false alarm rate stuff. This helps distinguish real targets from noise or clutter, pinpointing actual objects more reliably.
Okay, so we've got targets located in 2D, noise filtered out. We still need height and speed, right?
Exactly. The DSP isn't done yet. It performs Capon beamforming again for each detected point, this time to estimate the elevation angle. This is the height estimator figuring out how high off the ground each target is.
Gives us the z-axis.
Precisely. Then, another FFT is applied, this time across range bins for each target. This is the speedometer. It calculates the target's velocity, how fast it's moving.
So range, angle, elevation, velocity, all calculated right there on the DSP.
Yes. The result of all these steps is a refined point cloud, a set of points, each with range, angle, elevation, and velocity information, still on the DSP.
And then this point cloud gets passed to the Cortex-R4F microcontroller. What's its job?
The Cortex-R4F acts as the group organizer and tracker.
Yeah.
It takes the point cloud and first applies dbScan clustering, density-based spatial clustering of applications with noise. It's an algorithm that groups points close together. So if you have multiple people, it separates the points belonging to person A from person B. It identifies distinct targets.
Oh, okay. Groups the points into people or objects.
Essentially, yes.
Ah.
Then each of these identified clusters, each target, is tracked over time using Kalman filtering. This is the steady tracker. It smooths out the measurements and maintains a consistent track for each target, even if the radar data fluctuates slightly. Keeps tags on them.
So we've got these tracked clusters, these targets, but how does this become something the AI on the Raspberry Pi can understand? How do we get from a tracked cluster to knowing it's walking or falling?
That's the crucial final step on the radar board. The Cortex-R4F MCU transforms all that information range, azimuth, elevation, velocity, into 9 specific features for each target.
9 key features. What are they?
They are RX, RCCA, the range of position along the X, Y, and Z axis, then VX, V, VZ, the velocity along those axes, and finally AX, as the acceleration along the X, Y, Z axis.
Position, velocity, acceleration, the full dynamics.
Exactly. A comprehensive 3D picture of how each target's moving at that instant. These 9 features provide the rich description needed for activity classification.
And these 9 features get sent over to the Raspberry Pi 4 using UART.
Correct. UART is just a standard, reliable way to send serial data between the two boards.
And you mentioned it uses different features for different things.
Yes, intelligently. While all 9 are calculated and sent, the system uses the velocity and acceleration data Vx, v, vz, ax, I, as, that's 6 features, primarily for the activity classification part.
Okay, the movement dynamics tell you what they're doing.
Right, and the range information Rx, RSAA, TRAZ, the other 3 features, is used for the localization part, knowing where they are.
Titular separation optimizes things.
It allows the AI model for classification to focus only on the most relevant motion data, while the system still knows the precise location. And just to give you a sense of the setup, typically tinyRadar is mounted about 2.5 meters high, around 8 feet.
Okay, high up on a wall.
Yeah, often tilted down slightly, about 15 degrees. This gives it a good vantage point. Its field of view, or FOV, is pretty wide, about 60 degrees horizontally.
So 120 degrees side to side.
Right, and 20 degrees vertically. So it covers a good chunk of room.
And the range. How far can it see?
It detects objects reliably up to about 7 meters, which is roughly 23 feet, so suitable for most standard rooms.
And the resolution sounds quite fine-grained.
It is. Range resolution around 7.5 centimeters, 3 inches. Velocity resolution about 9.6 centimeters, under 4 inches a sec. It can pick up subtle movements.
So all these parameters, the frequency around 60.75 gigahertz, range, velocity limits, the 55 meters update rate, it all adds up to very detailed rapid sensing.
Absolutely. It's about translating those invisible electromagnetic waves into precise, quantifiable movement data. That's the language the AI needs to learn.
Okay, let's move to the brain now. The AI running on the Raspberry Pi. We know the radar meticulously generates those 6 key motion features, velocity and acceleration. How does the Pi actually understand what activity those features represent? You mentioned LSTMs.
Yes, long short-term memory networks, or LSTMs. And they are particularly, almost perfectly, suited for this kind of task.
Why LSTMs specifically? What makes them good for activity recognition?
It comes down to their ability to handle sequences and remember information over time. They excel at capturing temporal dependencies.
Temporal dependencies, meaning how things relate over time.
Exactly. Human activities aren't just single moments. They're sequences. Walking involves a repeating pattern. Sitting down involves a progression of movements. LSTMs have internal memory cells that allow them to remember relevant information from earlier in the sequence to help understand what's happening now.
Unlike, say, a basic neural network that might just look at the current instant.
Right, or even CNNs, which are great at spatial patterns, like in images, but needed those workarounds like slow-fast nets to handle time well. LSTMs are inherently designed for sequential data, like speech, text, or in this case, time series of movement features. They understand the story of the movement.
That makes sense. Understanding the story, not just snapshots. So what does the LSTM model in tinyRadar actually look like?
It uses a single-layer bidirectional LSTM, or bi-LSTM.
Bidirectional, what does that add?
It means the network processes the sequence of input features both forwards in time and backwards in time.
2 passes. Why?
Because context can come from both the past and the future relative to a specific point in time. Think about classifying a fall. Knowing in the movements before the impact, maybe a stumble, and the stillness after the impact provides a much stronger signal than just looking forwards.
Ah, okay. It gets the full picture around an event. Clever.
Very powerful for sequence understanding. This bi-LSTM layer has 96 hidden units, which gives it a good capacity to learn complex patterns from the motion data.
And after the bi-LSTM?
After that, there's a standard fully connected layer. This layer takes the process sequence information from the bi-LSTM and makes the final decision. It has 8 output neurons, 1 for each of the activity classes tinyRadar recognizes, falling, walking, etc.
So a powerful bi-LSTM core. How do you actually train this thing? Especially to handle those activities of varying lengths we talked about? That seems crucial.
The training process is indeed key. At each moment, the network receives input consisting of 6 consecutive frames of data.
6 frames. And each frame has those 6 motion features. VX, V, VZ, X, I is.
Correct. So the input at each time step is effectively a small block of recent motion data, structured as a 166 tensor.
Okay. But the variable length part, how does that work in training?
That's the magic. The model is trained using a data set containing examples of activities that last for different durations. Some samples might be short, like a quick jump, maybe 20 frames, 1.1 seconds, while others are long, like slowly going to bed, maybe 96 frames, 5.3 seconds.
So it learns directly from examples that activities don't all take the same amount of time.
Precisely. It's trained to recognize the pattern regardless of the total duration, which overcomes that old fixed window limitation. It learns flexibility.
And how does it know if it's getting the classification right during training? How does it learn?
It uses cross-entropy loss. This basically measures how different the model's predicted probabilities for each class are from the actual correct class label for that training sample. The goal is to minimize this loss, this difference.
Okay. And how does it adjust itself to minimize the loss?
Through backpropagation, through time, or BPTT, it's an algorithm that calculates how much each connection weight in the network contributed to the error, the loss, and adjusts those weights slightly in the right direction to improve the prediction next time.
Like tuning the network based on its mistakes.
Essentially, yes.
Yes.
Iteratively refining itself. The dataset they used was about 2.35 hours long with 769 samples, split 80% for training, 20% for testing. And they used PyTorch, a standard machine learning library, for the training. And another important detail, the training is stateful. Stateful. Meaning the LSTM's internal memory states, its hidden state and cell state, are carried over from one time step to the next within a single activity sequence during training.
Ah, so it maintains its memory or context throughout the entire activity.
Exactly. It learns based on the continuous flow, not just isolated chunks. For optimization, they use the Atom Optimizer with a learning rate of 0.01 over 50 training epochs, which are passes through the entire dataset.
Okay, so after all that clever training, the model is ready. How does it work in real time on the Raspberry Pi? Data comes in from the radar. Then what?
The Pi reads those 6 featured data points via UART. The trained PyTorch model immediately runs an inference pass, makes a prediction based on the current input and its memory state.
And does it just shout out the prediction instantly?
Here's another smart touch for reliability. It doesn't just trigger on the first prediction. The system waits until its confidence in a particular activity prediction gradually increases and crosses a specific threshold. They set it at 95%.
95% confidence, so it has to be really sure before it declares an activity.
Exactly. It builds confidence over a few time steps.
So what does that mean practically? It means tinyRadar isn't just guessing wildly based on a split-second movement. It's watching for a moment, building certainty, like a human observer would, before definitively saying, okay, that was a fall, or that person is getting out.
Precisely. This confidence threshold makes the output much more robust and reliable. It prevents triggering alarms based on momentary glitches or ambiguous movements.
Yeah.
It prioritizes accuracy and reduces false positives, which is critical if you're relying on this for safety alerts.
All right, let's talk about tinyRadar in action. We've covered the tech, the design, the AI. What about the actual performance? How efficient is this whole pipeline?
The numbers are pretty good. The radar board itself, the IWR6843, doing all that initial signal processing range, velocity, clustering, tracking, feature extraction, takes about 36 milliseconds per frame.
36 millers, that's pretty quick for all that work.
It is. And its CPU utilization while doing that is around 72%. So it's working hard, but efficiently for what it's doing.
And the Raspberry Pi doing the AI classification.
Even faster for its part. The LSTM inference engine classifies each data point it receives in approximately 10 milliseconds.
Wow, 10 meters.
Yeah, very low latency. And its CPU utilization is only about 20%.
So the AI part is actually quite light on the Pi.
Relatively speaking, yes. This low latency is absolutely vital for real-time applications. A delay of even half a second could be critical in detecting a fall, for instance. This system responds almost instantly.
And the accuracy again, remind us.
A 93% average real-time classification accuracy. And crucially, that's for multiple people activity classification.
That multi-target aspect seems huge. It's not just one person in isolation. It's handling the complexity of several people moving in the same space.
Exactly. Accurately classifying what multiple individuals are doing simultaneously is a significant step forward for practical HAR systems. It makes it usable in much more realistic scenarios. And perhaps the most powerful demonstration is the simultaneous localization and activity recognition.
Right, the where and the what together. How is that visualized or used?
The paper shows visualizations where you see a 2D map of the room relative to the radar. And on that map, it plots the location of each detected person. And right next to their plot, it labels the activity they're currently performing: walking, sitting, falling.
So you get this immediate combined picture.
You do. And think how useful that is. Imagine a caregiver and an elderly person. You don't just get an alert saying fall detected. You see who fell and where in the room they fell, while simultaneously seeing that the caregiver is walking towards them, perhaps.
That context is invaluable. It's not just an abstract alert. It's situational awareness.
Absolutely. Distinguishing between different people's activities in the same space is critical for effective monitoring, especially for vulnerable individuals.
The real-world applications here just seem enormous. We're talking continuous, unobtrusive monitoring without cameras or wearables.
It really opens doors. In healthcare and aged care, it's a game changer. Enhancing safety for seniors living independently, providing early fall detection, tracking routines, all while maintaining dignity and privacy.
Peace of mind for families, too.
Definitely. And beyond aged care, child monitoring, keeping an eye on kids' activities without constant visual supervision. Were they playing? Resting? Did something unusual happen?
And security. Detecting people where they shouldn't be.
Exactly. Detecting unauthorized presence in restricted areas, even through smoke or obstructions where cameras would fail. It's a very robust sensing modality.
Imagine a home scenario. Kids are jumping around, an elderly parent is resting. tinyRadar can tell the difference. It knows jumping isn't falling.
That's the level of discernment it offers. It's not just a simple motion detector, it's understanding the type of motion, attributing it to the right person and doing it privately. It's intelligent awareness. I really think this isn't just a small step. It feels like a foundational shift in how we can approach monitoring. Getting this critical information without compromising privacy changes the equation. It enables truly smart environments that are both safer and more respectful.
And what's next for tinyRadar? Where does the research go from here?
The team has clear future plans. One is expanding the data set significantly. More data, more diverse scenarios. That always helps make the AI model more robust and accurate.
Makes sense. Train it on even more situations.
Right. But the really big, ambitious goal they mention is achieving end-to-end edge computing.
End-to-end edge. What does that mean exactly?
It means getting rid of the Raspberry Pi, transferring the entire AI classification engine, the LSTM inference, directly onto the radar board itself.
Wow. So the radar chip does everything.
Yeah.
Sensing, processing, AI understanding.
That's the vision. A single, self-contained unit, sensing, processing, and intelligence, all in one tiny package.
What would be the benefit of that?
Huge benefits. Even more compact, lower power consumption, potentially even faster with reduced communication latency between chips. It makes deployment incredibly flexible. True embedded intelligence.
A single tiny device that sees, processes, and understands all on its own. The possibilities are kind of mind-boggling, aren't they?
They really are.
We've seen today how tinyRadar really bridges that gap between complex AI and real-world needs. It delivers on that promise of smart, unobtrusive monitoring that respects privacy while boosting safety.
It's a great example of clever engineering meeting intelligent algorithms on compact hardware. And, this technology, it's a testament to how miniaturization and smart algorithms can help us build environments that are safer, sure, but also just more respectful of our personal space, which is so important.
Absolutely.
But it does raise a fascinating question for the future, doesn't it? As these systems get even better, even more integrated, maybe even invisible, how will our own understanding of privacy and presence evolve? What does it mean when our environment understands our activity so intimately, even without watching us visually?
That is a deep question. How does our relationship with our spaces change when they become this intelligently aware?
Yeah. What are the new social norms, the new expectations? It's something to think about.
A fantastic and really thought-provoking place to leave it. We definitely encourage you, the listener, to think about how this kind of tech could apply in your world, your industry, your life, and just stay curious about these incredible advances in edge computing, AI, and sensing.
The field is moving so fast.
It really is. Thank you for joining us on this deep dive.